Thank you very much. So let me just quickly recapitulate what our problem is. So we have a reductive algebraic group over a field K, which is algebraically closed. And we choose inside G a Borel subgroup and a maximal torus. And this is it hard to read? I'll show you
a different chalk.
a different chalk. Okay. All right. Yeah, I see. Okay. Let me.
Oh, this was the chalk
try.
we used.
Yeah. So is that? It's maybe better, huh? Let me try. So this defines x plus in x. So these are the dominant weights in the weight lattice. So still difficult. Maybe if you turn off those. If those are turned. This is good? This you can read? Okay. Shall I maybe use color? Oh, color is much better, huh? Okay, this.
But this is already very much better.
Okay.
Color is much better. Yes. Go
Okay.
ahead.
Let me try
Yeah,
color for the moment. As long as there's still color chalk. Okay. So this is just underlying data. So TBG is a fixed choice. X is the weight lattice, and inside there we have the dominant weights. And then we have seen and we have proven that for each dominant weight there is an irreducible highest weight module. And these are pairwise non-isomorphic, mutually non-isomorphic, and they build a system of representatives of all the simple irreducible modules for G. And our problem is calculate the character of lambda, which is just a formal sum over all weights, and there you take the dimension of the corresponding weight space. So that is the T weight space in a lambda times e to the mu. Okay, as I said, this is unsolved as of today. Okay, so it's always a good idea to consider these representations not only as representations of the group, but also of the Lie algebra. So G is the Lie algebra of G. So just as a reminder, this is a subset in a set of derivations from Kg to Kg. These are the regular functions on the group, Kg to Kg. These are derivations. So this sits inside the linear endomorphisms. Kg, and these are the endomorphisms that satisfy the Leibniz rule. And these are the left invariant or right invariant, it's the same. Derivations, the left invariant derivations. So, and this here is the set of all delta inside the endomorphisms that satisfy the Leibniz rule. Let me just write it down because I explain. I mean, this is of course very well known, but I tell you about an additional structure that we have in positive characteristic. So the linear endomorphism that satisfy this Leibniz rule. And you know that the composition of two such endomorphisms in general does not satisfy the Leibniz rule. The commutator of two such endomorphisms does. And this makes this into a Lie algebra, this set of invariant vector fields, or invariant derivations. So these are all vector fields, and these are the left invariant ones. But there's an additional structure that we will need further on. Namely, it's this Lie algebra is what it's called a P Lie algebra. So where in case P is the characteristic of the field K and it's bigger than 0, in this case Lie G is a P Lie algebra. So what does that mean? It comes with a map which is the pth power, and it's constructed as follows. So if delta is a derivation, then delta to the p, and this is just the pth power of delta considered as an endomorphism, this is a derivation as well. I mean, this is an easy exercise. Again, it's kind of the peculiarities of the Frobenius map in characteristic P. So the Lie algebra comes with a pth power map. And this pth power map has a special notation to denote this map as, so this goes from G to G and sends X to X bracket P. So this is the usual notation for this pth power map. Well, the reason is that, I mean, a pth power in a Lie algebra doesn't make sense. Pardon me?
It's a composition or power?
This is a composition of endomorphisms. Yeah, this is a p-fold composition of endomorphisms. So, and of course, you cannot do that in an abstract Lie algebra. And also, I mean, later we will consider the universal enveloping algebra. And then for each Lie algebra element X, we have an honest pth power in the universal enveloping algebra. But this won't be this one. This pth power stays inside the Lie algebra. So it's an additional structure that you only find in characteristic P. Okay, this is not linear for K, but only for the field, the fixed, the prime field of inside K, right? Because the pth power is not it's not a linear map of the field, but only for, of the prime field. Okay, so this is the Lie algebra, and if M is a G module, then differentiating the G module structure yields yields a G module structure on M. So this will be a G module. Just as a reminder, I mean the structure of M as a G module is given by a map from G to GL M, and so this is the map. And if you differentiate this map and evaluate it at the identity element of G, then you get here a map between tangent spaces, and these left invariant vector fields can be identified with the elements of the tangent space at any point. For example, the identity element, the neutral element in the group, and this goes into the endomorphisms of M, which is the tangent space of GLM at the identity matrix. And this yields a homomorphism of Lie algebras, and so M acquires the structure of a G module. Okay, so let me be, thanks. Let me be more specific in an example. Okay, the example is the Lie algebra of SL2. So this is SL.
This will be a homomorphism of P Lie algebras.
Pardon me?
This will be a homomorphism of P Lie algebras.
Of yes, yes, absolutely. This is right, right. So yeah, I should have said that. This is a homomorphism of P Lie algebras, which means this is even what is called. It is even a restricted. I.e., that means x to the p minus x to the p x by 0 for all x in G. So this is the pth power in this is the pth power in the universal enveloping algebra of G. The universal enveloping algebra of G, and this is our additional assumption. So this will act by 0. This is not true, of course, for any module of the Lie algebra G. So there are some modules, very many modules of the Lie algebra that are not restricted, where this element does not act by 0. But if the module comes from a module for the group, it will automatically be restricted. Okay.
And vice versa.
Vice versa. No, that's not true. Vice versa. There are some modules for the Lie algebra that cannot be lifted. So an example, SL2, SL2K. So in this case, we look at the module we had before, kxy, polynomial ring in two variables. So we had the group acting on this. Let me write down the action again so that we can see what is going on. So if this is an element in GL2 K, so in the group, so this will have determinant non-zero determinant. GL, no, let me take SL. Let me take SL2. So determinant 1 matrix. This acted on x to the I, y to the j as follows. So this is ax plus cy to the I times bx plus gy to the j. So that was the action. And if you differentiate this action, you get the following. For SL2, the diagonal element 1 minus 1 of trace 0 will act as the following operator. It will act by x dx minus y dy. The upper triangular matrices, this will act by x d dy, and the lower triangular matrix will act by y d dx. So you can check this as an exercise. That these really give the operators on this. This is the differential of this action for the Lie algebra, y dy dx. Okay, so but now concretely, what kind of modules do we get? We saw that this big space here, Kxy, breaks up into a direct sum of homogeneous components. These are submodules, and this is actually a direct sum of all the Weyl modules that we found in the first lecture. So let's look at these modules as modules over the Lie algebra, and you see a new phenomenon occurring, so emerging. So so we defined H0 n to be K, so the homogeneous component of total degree n. So this is generated by x to the n minus 1 y up to y to the n. This is a basis, and you see the operation of the three matrices of SL2 is very easy to calculate in this matrix. But now let's look at the simple module at P. This we identified for the simple module for the group as being two-dimensional and being generated by x to the p and y to the p inside H0 P. So this is a submodule for the group. But now if we look at the action of SL2, we see that each individual component is it's actually the trivial module. So this splits further. So this is so this is stable for SL2. I mean, check here. So if you differentiate this by with respect to x, this x to the p, you get p times x to the p minus 1, but p times something is 0 in characteristic p. So and differentiating with respect to y is 0 anyways here. So this is everything works operates x by 0 on this space and on this too. So this LP is just the trivial module plus the trivial module, a direct sum of two trivial modules for SL2. Can you still read that? Is that?
There's more chalk here.
Yes. Okay. This maybe. Let's see. Okay, this is better for SL2. So what we see that differentiating a simple module might produce a non-simple module. In characteristic P. I mean, you can check in characteristic 0 that these H0n are irreducible for the Lie algebra. I mean, look at these actions. It's even simpler than for the group to check that this is actually irreducible for the action of these three differential operators. Okay. Well, this is bad news in a sense, because it tells us that it's not so easy to study simple modules for the group as modules for the Lie algebra, because they don't stay simple anymore. And moreover, we lose the information on the character, because the character of these simple modules LP or LN is calculated via the action of the torus. So in addition, we lose the character. as p lambda, the weight p lambda, this by differentiating, because I mean we write, so this is written additively in the group, right? But it's actually a product, a p-fold product of a character. If you differentiate it for the Lie algebra of t, we get 0. So it's a 0 character. For the Lie algebra. So, I mean, these characters, they coincide. Okay. So we lose the character. We'll find a way around that problem in a bit. But first, so we can solve all these problems. And this is the topic of today's lecture. We will be able to translate the character problem fully into the Lie algebra. But we need some additional ideas. So let me start. Okay. So let's define U, or U restricted. U restricted to be the following quotient. This is the universal enveloping algebra of the Lie algebra divided by the ideal generated by everything that acts by 0 anyways on all modules that come from the group, x to the p minus x to the p. So this is the ideal generated by these elements. X is in G. So what, yeah, this I guess is readable. Okay. X in G. This is the restricted enveloping algebra. And inside there we have U minus, U0, and U plus. These are the images of the universal enveloping algebra of the Lie algebra of the Borel. I mean, recall that our choice of the Borel, it doesn't really matter. Our choice of the Borel corresponded to the negative roots. U of b plus. Yeah, let's put a minus there so that it's kind of clear what is meant. And then the restricted enveloping algebra, it's not difficult to prove using the PBW theorem. It's just a tensor product of these three subalgebras. So we have a triangular decomposition, and we can play the usual game with the highest weight module. So if lambda is in X, and these are still the characters of the torus of the group, then we have K lambda, the one-dimensional T module. So this is so it's actually a one-dimensional B module, right, for the Borel, or let's say a B plus module, where the unipotent radical acts trivially, and so we consider it as a module for right. So that was a mistake here, right? Sorry, I mean, this of course is not a Lie. So U minus is the unipotent. So this is the Lie algebra of the unipotent group, which by by chance I denoted by U minus 2. I'm sorry about this confusion, but let me stick to it. So these are the algebra versions of these groups. I'm sorry about this this possible misunderstanding. I think we don't need that anymore.
That tensor product you've written there, why should that be U rest and not U?
Oh yeah, it's true. Oh yeah. So it is.
It's already the quotient.
It's already, yeah. These are the images in this quotient. It's of course it's also true for U, but then it descends on the quotient. You have to check that it really descends on the quotient if this is nice. But I mean, this is this quotient can be done in each component individually. So PBW theorem is behind that. So and then we can consider it as a U0 U plus module. So this is a U0 tensor U plus module. And then we can induce, and we get a module Z lambda, which is so U, the restricted universal enveloping algebra, tensor U0, tensor U plus K lambda. Okay, and so this is a Z of lambda, and this is sometimes called a baby Verma module. So it's an analog of the Verma modules that you might know in the theory of representations of a semi-simple complex Lie algebra. But it, yeah? Pardon me?
K lambda.
K lambda?
What do you mean by that?
Ah, yeah. So lambda is a weight of the torus, and this is also a character of the Borel. You know, where the unipotent, you can this is lambda determines a one-dimensional representation of the torus, and you can extend it to a one-dimensional representation of the Borel by letting the unipotent radical act trivially by the identity. So this is a one-dimensional B plus module. It's called K lambda because it's one-dimensional. And then you induce and you get what is called a baby Verma module. It's called a baby Verma module because it's finite dimensional. It's quite small. But it's not growing, so it's called just small. Or starting to run away or so, no. Okay, so the dimension is known, and even the character. Well, okay, we cannot really talk about characters on this level, but the dimension of this is known. It is p times p to the number of positive roots. P to the number of positive roots. So why is that? This is just the same. I mean, this is a tensor argument as a dimension of U minus. So it's completely independent of lambda, and U minus is a quotient of the universal enveloping algebra of this Lie algebra. And if you look what your quotient out, I mean, now take a PBW basis, and you can, so it's powers of basis elements of Lie U minus, but each pth power you can write in terms of the Lie algebra basis again. So each pth power can be reduced. So you get everything from power 0 to power p minus 1 for each basis element. And so this is what you get. And
Lambda is rho with the Steinberg.
No, lambda is arbitrary.
No, when lambda is rho,
Well,
is it simply the Steinberg or?
no, it's right. When lambda is rho, the Steinberg would be a group, a module for the group, not for the Lie algebra. So it would be the Wahl module so it would be this H0 rho or so I mean here we are talking about the Lie algebra and not the group.
But does it
No,
come
but what I
from
mean is
some?
it comes from, that's what I'm saying. It's rho, P minus one
right.
rho. The global sequence is the Steinberg. The weight also is matches and the dimension also matches.
so, I mean, in terms of rho, is that, so you are asking if this is what we get if we differentiate the Weyl module at rho. I have to check. I'm very uncertain, so I have to check
But
that.
these are not in general
that's-
obtained by differentiation.
No, in general, certainly not. So these are not obtained by differentiating the Weyl module, even though they are constructed. The Weyl module is induced from this representation, and this is the baby Wörmer module is also induced in for this representation, but one for the group, one for the Lie algebra, and this is not compatible with differentiating. For example, the Weyl modules, they have arbitrary large dimension, right? The higher lambda gets, the bigger the Weyl module gets, but those have all the same dimension. Okay, so a fact that is needs some proof, but I mean it's kind of not so important for this series of lectures. This has a simple head, so a unique irreducible quotient, and this we call L bar lambda. So L or L hat lambda. L hat lambda is the simple module with highest weight lambda for the Lie algebra. So at the moment it has nothing, I mean there's no immediate connection between L of lambda and L hat of lambda.
Can I ask you?
Yeah.
Is U-res a module Swift?
Yes, it is. So, I mean, the by the adjoint action.
Yes.
Yeah.
And so this Z lambda will be a module Swift. Will Z lambda be a module Swift?
For the group. So, the problem is, let me see. The problem is this lambda. I mean, here it occurs only as a differentiated weight. So if we, so if example for the, so you cannot recover lambda from K lambda as a module of the Lie algebra, because maybe let me write that down. So now maybe I try the green one. So, oh, that's readable, right? Again. So another fact is that Z lambda is isomorphic, or I mean even the same as Z lambda plus P times mu for all mu n in X. Because this plus P times mu just vanishes when you consider it as a module over the Lie algebra. Okay.
So when you said that that's the simple module with highest weight lambda for the
Yes.
algebra,
Ah.
it's very heuristic, right? It's
Yeah,
not
yeah. So the term highest weight here at the moment doesn't make sense, but it will make sense in a moment. Okay. So, I mean, I guess most of you know some version of highest weight theory, for example, for complex Lie algebras or Kac-Moody algebras, and this looks very familiar. But the problem is that at this level, there's a lot of tiny technical problems. One of them being that there's no notion of highest weight, because these weights they're only defined modulo p. But we'll we'll recover highest weights theory in a moment, but for now, we have to stick with this Lie algebra notion. So what do we do now? Okay, so claim. So if lambda is in x, then x plus, then we can differentiate the simple highest weight module for the group. So there's no head here. There's no head. This is semi-simple. At the G module. So we saw that in this one example, we have seen that LP is the trivial module plus the trivial module for SL2. Right? This we calculated. So it's definitely semi-simple. It's semi-simple as a G module, and the proof is not so difficult. Let M in L lambda be a G submodule, and suppose G is an element in the group. Then I claim that G of M, so Gm, that's what the subvector space you obtain by applying the group element to this vector space M is again a G submodule. Or simple calculation. So if you have X in the Lie algebra, then you have to check. You want an M in M, an N in N in M. Then if you look what happens when you apply the operator coming from the Lie algebra to Gm, then you can write this as G to the minus 1 x G M. And this is the adjoint representation of the group on the Lie algebra. So this is again an element in the Lie algebra in G. So this is an element in M. So this is an element in Gm. So you see Gm is stable under the operators coming from the Lie algebra, so it's again a submodule. So so that means that means the following. Well, just so if M is simple, then Gm is simple as well. It's a simple submodule. Well, because I mean, if Gm has a submodule, by applying G to the minus 1, you would get a submodule of M, right? So it's very it's very simple, and this implies that the socle of L lambda, the socle, of course, I mean, taken inside the category of modules for the Lie algebra. This is a G submodule. It's a big G. It's a big G submodule. Right, because applying G makes a simple submodule into a simple submodule. So I mean, as L lambda is a simple group G module, this must be the same. So L lambda is semi-simple. Okay, well, that's already something. It's semi-simple, and okay. Let me leave the definition of Z lambda on the board for just one moment, because we need that now. So they're suitable. Exist a homomorphism. Maybe that's difficult to read, or is it okay? It's fine?
It's okay.
Is it? It's not so good?
Yeah.
Okay. Hmm?
White
Um,
is good.
Shall I try white again? A homomorphism. So there exists homomorphism with, oh, that's good, right? This is a phi lambda from z lambda. Or is it? It's readable?
Yes.
Okay. To L lambda sending one tensor 1, this element 1 tensor 1 to V, where V is in L lambda, the lambda weight space, and is a generator. Well, just because V is stabilized, the line through V is stabilized by the Borel, and so it's stabilized by U0 plus U plus, and it just, if you differentiate it, it's the module K lambda, and this is just an, just the universal property of a tensor product that gives you this map sending one tensor 1 to V. So now we know two things. The hat of Z lambda is simple, and L lambda is semi-simple. L lambda is semi-simple as a G module, as a Lie G module, as a module for the Lie algebra, and this implies that the image of phi of phi lambda, the image of phi lambda, is simple, right? It's a semi-simple. It's the hat. This hat is a simple hat. This is semi-simple, so the image must be simple. Okay. This is an important statement that we now use. So now you will see in a second what all this amounts to. Namely, now I prove the following. So this is a proposition. We are again taking a dominant weight. And suppose lambda is restricted. Suppose lambda is restricted, and restricted for weights means the following. If you evaluate lambda on each positive co-root, you get something which lies above 0. That's just lambda in X plus has all the, is already, it's positive, but it must be smaller than P for all positive roots alpha, a positive root. So this is a positive root. I haven't defined R plus alpha, positive roots alpha. Then L lambda is simple as a G module. Okay, we prove this in a moment. So at least we know that for these weights, the simple group module stays simple when you differentiate it. We have seen that for SL2. Recall that we have seen that H0n is Ln, and this is simple for the Lie algebra SL2. We have seen it because these operators x d by dx and d by dy, they are non-zero. There's no exponent p coming down, right? They're killing this. So we're staying in a kind of safe area. So we've seen it for SL2, and now it follows for arbitrary group. So by the way, it's a quarter past maybe. Okay. Maybe let's finish this and then have tea. Yeah, we will have a tea break. Yeah. Okay, let's finish this proof. That is won't take too long. Okay. The proof is as follows. So we know that there's a simple submodule for the Lie algebra inside L lambda. It's the image of phi lambda. This sits inside L lambda and is a simple submodule. So let L denote this image. So this image of phi lambda. This is, I mean, if you look at it, the image of phi lambda must be the Lie algebra module generated by V. This is just U rays applied to V. This sits inside L lambda. And enough to show, so we have to show that this is everything. That this is everything. And so it is enough to show that L is G stable. Right? So we still have the group acting on a lambda. And so if L is G stable, it's a G submodule for the group, so it must be everything because L lambda is simple. So it's enough to show that L is G stable. So for this is enough to show that G applied to V is in L for all G in G. Because then, I mean, then right? So so GL is generated by GV. So for all G in G, so if G is in V plus, then GV is just a multiple of V, so this is okay. I mean, the Borel stabilizes this line. So, and now the Wald group comes into play. Let me. Let me see this. I think I broke that a little.
Could you try that?
Ah, yeah, okay. That is, yeah. Thanks. So, let us look at the Wald group of this group. This is the normalizer of T in G divided by T. This is the Wald group. And for W in W, choose W and NGT, W point, and NGT a representative. W dot. And then you can calculate that. Then that's an easy calculation that W dot M lambda equals M W of lambda for each G module M. And each weight lambda in X. So this is an easy calculation. So W, the Wald group, acts on T, of course, by conjugation. Then it also acts on the weight lattice. And so this is an easy calculation. So as an aside, all characters are W invariant. So now our claim is that W of V as before is in L as well, but this W dot V is W dot V is an element in L W of lambda. So this is a claim that we want to prove. It's not difficult to prove. So first we look at alpha, a simple root. Then in this case, as alpha dot, is that? Let me. Okay. Let me just write it here. So everyone can read that. So then as alpha dot V is in L, and this is an SL2 calculation. And now our assumption that lambda is restricted comes into place because schematically
Piece of weight lambda.
V is of weight lambda.
What is the problem? W is the
Say it again.
the weight of W needs to be W lambda.
Yeah.
I'm sorry, what is the meaning of writing capital L sub W of lambda? Because capital L is not a group. That's what you are trying to show, right?
Capital L is the image of V.
No, but it is bigger one. L lambda is
You're right. Okay.
capital
Right. Right. Okay. What is right? So L is a module for the Lie algebra. So and we don't have LW lambda. Right. So. Okay. Actually, we don't need that so much, but let's write it like this. That's good enough. That is good enough. So let me claim. Okay, the claim, of course, is W dot lambda V is in L. We know it's certainly in L lambda W lambda. Okay, so what if we take a simple root? Then I claim it's an SL2 calculation. So if you have to weight lambda here, you have to weight S alpha lambda here, and the distance between these two here is smaller than P, and this has here this is so L lambda lambda. The dimension of L lambda lambda is 1, and by invariance, the dimension of L lambda S alpha lambda is 1 as well, by W invariance of the character. So now the Lie algebra acts from this weight space to this weight space. I mean, this is explicit SL2 calculation, and I mean this what you get here when you apply the Lie algebra to this highest weight is an irreducible SL2 module. But since everything is smaller than P, this is like in characteristic 0, so you will reach this one-dimensional space at the end. So, I mean, we even showed that L lambda S alpha lambda is contained in L.
With the x minus alpha operator, our
Yeah, right.
lambda plus alpha. Our lambda plus alpha.
And so these reflections, so this now means that S alpha dot L is inside L, or is the same as L. So since these reflections with the simple roots, they generate the whole Weil group, this means W dot L gleich L for all W L and W as W is generated. Okay. Now what we have proved, so it's very easy that elements of the Borel stabilize our module. Elements of representatives of the Weyl group stabilize our module. And now you take Brühar decomposition, and elements of the Weyl group, representatives and Borel generate the whole group.
Example B, that little b, that's in capital L. What about other vectors?
Here.
Oh, it is that what I am thinking. Capital L, what is
Just the image of
Yeah. So
other things commute with this alpha. The way the other vectors are also in that.
So the idea. So the idea was to L is a simple module for the Lie algebra. It's not a priori stable under the whole group. This is what we proved now, is that this simple module is stable for all elements of the group. It's a G module for the group G, and we proved that for the Borel and for representatives of the Weyl group, which is enough.
But we are building for that little b.
Right.
Lambda.
Right.
You have not other vectors.
Right.
We want
So.
a commuter.
Enough to show that purge only the G is set down.
It's enough to show that GV is in L, because GV is in GL and L is simple. You know, I mean, if they have non-zero intersection, so it must be the same. Okay, so let me finish this. The Brühar decomposition. So this yields G is generated by B plus and the set of W point or chosen representatives. So GL equals L for all G and G. Okay. And this is the proof. Okay. It's a good time for a break?
Yes.
Okay. Plus length of x, and then here we have length of w plus length of x minus 2, then minus 4, minus 6. I mean, so this everything is plus 2, plus 4, plus 6. So these should be ranks. And a free-graded S module a free-graded KT module looks as follows. So it has a generator, say in degree minus 6, and then has a T times this generator is a one-dimensional generates a one-dimensional subspace in degree minus 4. Then there is something minus 2, something in 0, 2, 4, 6. And if we have a direct sum of those, then it might be that there's some, say, 2 generators in degree 8. So these generate these subspaces, and so on. And this goes up to infinity. So this would be a picture of a graded free module of rank minus 6 plus minus 8 plus minus 8. So v to the minus 6, v2 plus v2, v to the minus 8 would be the graded rank of this module. And now the duality is just that it's just made in such a way that it flips around these the axis, the critical axis. So this could be a picture of BWX, and now sitting inside as a sub module is BW lower bracket X. So BW lower bracket X. So maybe if you allow me, maybe you have. I want to be a little bit more efficient with space. Just let me delete these uppermost elements. So the submodule will be generated in degree +4. And then you will have 2 generators in degree +6. So the important thing is, I mean, that it's symmetrically organized. So it's a dual module with up to a shift, up to a constant shift. Now there's an injective map from here to here, and there are certain strata for the space of all possible maps. So, for example, I mean, the question is, how canonical is the choice of these generators? It is certainly not canonical, but the vector space generated by these 2 generators, this is canonical. I mean, this is lowest degree. There's no choice. But once you have chosen 2 generators, you defined this submodule, this free submodule, and you know it splits. But then you have to make a real choice for this generator. It's an element in a quotient, right? So this is not canonically. This is only defined up to everything which comes from lower degrees. So and the same here. Here you have a rank 1 submodule that is canonically generated, and then you have a rank 2 submodule in the quotient. So for a generic injection will have the property that this canonically defined submodule is not contained in the canonical defined submodule here. So think of this as a hyperplane in space, and you have a line, an injection of a line. Canonically, this line doesn't lie in this in this space. So canonically, this is not contained in the submodule. But then you can, I mean, then it has a component. So it has a component here, and then you can divide by an appropriate power of t, and choose this as your sort of canonical second generator. In other words, with a generic map, this module would sit inside here. But then, since these are not canonically defined, you can choose multiples of these canonical generators for these generators, and well, in the end, so let me get some blue color. This is really a beautiful, important picture. So the canonical, the generic injection of such a submodule here would look like this. You see, it's kind of symmetrically organized in a kind of pyramid form. For a generic map, for almost all maps, this will be the case. Now, let me tell you, if this is the case, you proved Castells-Lustig conjecture. And why is that the case? So, suppose you prove that all these injections of BW lower x to BW upper x have the property that these generators are kind of organized in this pyramid form. So what happens? What happens now if so the important property was, let me write it down for a second. That was what we want to check, is that BW x is generated in degrees strictly smaller than length of W plus length of x. Suppose this is not the case, and we have a generator at this critical limit, then by duality, we have another generator of this submodule in the same degree. And by this pyramid form, these two generators coincide. They're the same. But this would be absurd, because BW X to BW X to BW delta X is a short exact sequence. So if there's a generator of a direct summand coinciding with a generator of a direct summand here, then this is not a projective cover. It's not, I mean, this can be deleted and will still be a free module mapping on this. So it would be unnecessary. But since we constructed projective cover with a minimality property, this cannot happen. So that would mean once you know that there's this pyramid form, such a situation cannot occur. So everything is generated in degrees smaller than length of W plus length of X. That would solve it. And you see, this is a kind of beautiful generic picture. So the only thing that you have to prove is that this injection satisfies this, is generic. It's not degenerate. It really gives such a picture. Let me finish with one last remark. You can now look at what happens when you delete, when you look at the quotient of this injection. Then you get a torsion KT module, which is again, with a slightly different line of symmetry, which is kind of organized in this pyramid form. Right, so it could also have some line here in general. It would look like this, and the parameter T would act as an operator of degree 2 in this direction. And this torsion module, if it's organized in this pyramid form, satisfies the Hart-Lefschetz property. Because the Hart-Lefschetz property says that in degree -6, for example, on the primitive, on the degree -6, the operation of T to the 6 is an isomorphism between degree -6 and degree, now the line of symmetry is -1 here, and degree +4. The reflection hyperplane is -1 here. So it would give a symmetry, an isomorphism between here, and between here, and between here. This is the Hart-Lefschetz property in geometry. So once you prove this in the realm of circle bimodules or moment graph sheaves, you're done. And this property is exactly what Ben Elias and Jody Williamson proved. The Hart-Lefschetz property for circle bimodules.
So why is this not complete argument? Something you have to do something about the injection.
Yeah. So
I missed that point. So what is incomplete in the picture?
So what I wrote down here is the following: it is BW upper X divided by BW by this kernel. So it is kind of this module, but over polynomial ring in one variable. Yeah, but okay. So and I claim one should prove that this satisfies the Hart-Lefschetz property. Because if it satisfies the Hart-Lefschetz property, this genericity of the injection is implied. This is an if and only if statement. it's an if and only if statement. So what it could also be, I mean, if so this is a completely different picture than, for example, let me show you lower rank situation. If you have a module M and KT torsion module, say with degree M minus 2 is 1, the dimension of M0 is 2, and the dimension of M2 is 1 again, then there's two possibilities how it can look like. So it could, right, so it could be either as a KT module look like this, so the operation of T is like this, right? It has two, it's a direct sum of two submodules of dimension 2, or it looks like it has a trivial submodule and then a submodule of dimension 3. And this is the hard Lefschetz situation. This is the good situation. It's completely pyramidal, you know, and this is the bad degenerating situation. And if you think of this as a quotient of two free modules, then the one submodule would sit here, and the one submodule sit here, and it would not be the generic situation that we constructed before, because then we said, so this submodule is uniquely defined, and this submodule is uniquely defined. So these are two lines, and they should not coincide in a generic inclusion. So if you have two lines in a two-dimensional space, they should be in general position, which means that this line is actually here and generates the trivial module. So from this point of view, all these problems are extremely beautiful, and you know, it's about showing that one line is not contained in a plane, which is almost always the case. Except in characteristic P, when you know everything is finite anyways, and chances are it might be contained in a plane. You know, in characteristic 0, the probability is 0, right? So it's true. In characteristic P, the probability might be 1/2 or something, or something. So it's or a third or so. Okay. Okay, let's have a break. Yeah.
We can
Right.
go on further.
Okay. Okay, so let me just clarify a few points that came up in the break. So this is the principal conjecture. And it's implied by the hard Lefschetz property of the quotient when you consider it of B bracket x, BW bracket x, and BW upper x. Of the quotient when you consider it in a situation where you have a polynomial ring of rank 1. This would be the hard Lefschetz property. And as I said, this is what Ben Elias and Jordi Williamson proved in characteristic 0. But it's not clear in characteristic P. And in fact, to be very honest, they didn't prove the hard Lefschetz property in this situation, which is a local situation because it corresponds to X. They proved it in a rather global situation, but which should be more or less equivalent. So there's a local hard Lefschetz and a global hard Lefschetz, and they proved the global hard Lefschetz, where this is the local hard Lefschetz. But I think their arguments also work in this local situation. So that was one remark. And then these Braden-McPherson sheaves they occur in a different situation. So let me say a few more things. So if you form the global sections of the Braden-McPherson sheaves, then I might have mentioned that before. You can construct an action of S tensor S. So one copy of this S is just an ordinary action because we are working in an S linear category anyways, and the other action is a kind of twisted action of the symmetric algebra. I think I have defined that. And then a theorem
By the same W, twisted by the same W, right?
not by W, but by, so this is given by a map sigma tensor tau, and sigma is a map from S into the structure algebra of our graph, sending a lambda to the tuple W of lambda. Sorry, X, I should say now X of lambda, because Z sits inside this direct sum. So on each stalk, lambda acts as multiplication by the parameter of the stalk applied to lambda. So that is the twist, and a theorem that you find in my paper Combinatorics of Coxeter Categories. It's appeared in the transactions paper. So is that as an S bimodule, this is the indecomposable Zergel bimodule. That I denoted by BW, without a curly B. This is the indecomposable Zergel bimodule. This is a nice result because it gives you a way to construct this indecomposable direct sum directly. Also using an algorithm, but you don't have to decompose a tensor product.
This PW is the direct summand of that.
Right, and this is, so it's a direct summand of a Bethe-Samuelson module corresponding to a reduced expression of W. So this is a direct summand, even. Uniquely determined.
So the modulus not depends on the reduced expression, the decomposable thing is, that does not depend on VW.
Right, so this depends on the reduced expression, but the isomorphism class of this kind of biggest direct summand doesn't depend on the choice of a reduced expression. That is Zergel's theorem. So what Ben Elias and Jordi Williamson proved is a Hart-Lefschetz property for Zergel bimodules. They use the construction. I mean, they have to use the construction of Zergel bimodules. So they're looking at tensor products and prove that by induction on the length of W. Let me see. So what should I say? Okay. Now you can study this Hart-Lefschetz property in the same way as we did for BW. You can study this on the Bethe-Samuelson module, just the same way. But it won't satisfy this Hart-Lefschetz property just because there are shifts occurring. So we know that this is a direct sum of Zergel bimodules, say Wi shifted by some ni's. I mean, there will really shifts will occur. And as soon as you have a direct summand with a shift, this Hart-Lefschetz property is destroyed. It doesn't have the same center anymore. But now the trick is the following. So we kind of know the Hart-Lefschetz picture in characteristic 0. I mean, we know this decomposition is given by the Kashtan-Lustig algorithm, and we know the shifts and everything, and we have a kind of intricate Hart-Lefschetz picture in characteristic 0. It might look like as follows. So we have here a component with this reflection hyperplane. Then we have a component with, say, this reflection hyperplane. And then we have further components. It looks in characteristic 0. It looks like this. And the important thing, the one thing that is for that is really necessary for us, is that we don't have anything sitting on one of these reflection hyperplanes. Right? That was the decisive thing. Sorry. Sorry. I mean,
Could be trivial sort of thing in bigger module.
pardon me?
In the bigger module, it could be.
Right. That is. Thank you. That is exactly what I want to say. I mean, this occurs only if x equals w. So this if this corresponds to a stalk of bwx, then this implies x equals w. So what I want to say is that that this situation where we have, the generator of the bigger submodule and the generator of the smaller submodule coinciding might appear, but only in the situation where the stalk that we look at corresponds to the parameter. That might appear. So what Jordi in his counterexamples, now in principle, I mean, to boil it down to a principle, what he did is the following. He looked at exactly such a situation. And he did that over the integers. So you can define the Bott-Samuelson modules over the integers. And then, if I say the generator of the bigger module coincides with the generator of the submodule, then this is only true in a field where you can kind of divide numbers. So he found a situation where you get here, say you have the generator V and the generator W, W belonging to the submodule, V to the bigger module, and he found the number C such that CW equals V. So there's an integer involved. In characteristic 0, it doesn't matter. I mean, then you can renormalize your generator in any way you want. The important property is that C is not equal to 0. And now, so C is an integer. Now, if you have a prime dividing C, then you see here's something going wrong. I mean, it kind of splits and it gives a degeneration, a non-splitting of a circle bimodule. So, in any case, let me start from before. Let me explain it once again. This decomposition pattern here is determined by the structure of these Hart-Lefschetz operators. And we know that in characteristic P, the decomposition is the same as in characteristic 0 if this Lefschetz structure is the same. As soon as something degenerates here in this structure, you know that Lustig's conjecture is not true anymore. And Jordi found a very specific situation with a very ingenious argument where he found a number in exactly this limit situation, a certain number that he constructed using Schubert calculus, in fact, from which he knows that each prime divisor of this number yields a counterexample to Lustig's conjecture, because the Lefschetz property won't hold anymore. Right. So how did he? I mean, so how did he find this number? So I'm not sure if I have a good way of explaining. No, I do. I think I can explain a little more about the approach. So. Yeah, so so fix a reduced expression. Fix a reduced expression. Then this defines a Bott-Samuelson module. So this, as a reminder, is just this tensor product of the Sergel bimodules corresponding to these simple reflections. This is a Bott-Samuelson module, and this, as before, yields a map from this submodule X to the stalk of the Bott-Samuelson module for any X in W. So what you can do now is, because this construction is so explicit, you can construct a basis of these bases, a basis here and a basis here. And you can construct explicitly, so construct bases. So for this you can, I mean, I did that, I did something similar in the upper bound paper. So that appeared in Duke. This gives some basis. Or in a more diagrammatic fashion, this was also studied by Lebedinsky. Nicolas Lebedinsky, a student of Raphael Rouquier. Jordi mentions his results in his paper. So you construct a basis. Pardon me?
Construct a basis
for this space and for this space. So this is kind of explicit.
Which is dependent on the map. You get a basis. You get a map also with respect to this basis.
Right. No. The map is canonical.
Okay.
So
Write down a matrix.
yeah, then you can write down a specific. You can construct a specific matrix. So this gives you a matrix A in these bases. Then you consider this matrix A over a polynomial ring in one variable. And this matrix, of course, from this matrix you can read off the Lefschetz pattern.
This you are doing over integers or any field?
This actually lives over so the entries are integers. So this is actually, yeah, thank you. This can be done over the integers, but it also has powers of t. But this matrix, the co-kernel of the corresponding map, gives you is the one you should study, where you should study the Lefschetz property, and so you want to compare the structure of this matrix over a finite field of positive characteristic with the structure of this matrix over the rationals. Because over the rationals, you know everything is proven, and this is what you want. And now, in order to show that the Lefschetz structure, Lefschetz patterns are the same, you have to look at certain ranks of certain submatrices here. So you are led to checking the rank of specific submatrices here. So, I mean, this matrix, I mean, if you so this will be an isomorphism over the quotient field, because the co-kernel of this map is a torsion module. So if you invert T, then this is an automorphism over any field. Is that true? Yeah, over any field, and over Q, it can be written as a block matrix where each block kind of has a it defines one of these Lefschetz indecomposable Lefschetz patterns. So here, in each block, you have powers of the so different powers of the parameter in the variable in the polynomial ring. And the Lefschetz property kind of depends on which degree the corresponding basis elements have. So if this has degree n and this has degree m, then t to the L1, I mean, what do we say? So let's say, so this should correspond, I mean, to a Lefschetz pattern that is kind of symmetric around one. You see, this is one basis, and this is the other basis, and so that the ranks and the powers of T should have a certain, should satisfy a certain relation. So you are led to studying ranks of submatrices, of certain submatrices, and as long as these ranks of these submatrices are the same in characteristic P as they are in characteristic 0, you are done. Then you proved it. So
In that one sentence, when you say as long as?
As long as the ranks, so you specify certain submatrices here. And as long as the rank of these submatrices are the same in characteristic P as they are in characteristic 0, you're done. That means you calculate determinants of a lot of submatrices, and you have to exclude all prime divisors of these determinants.
Actually, it's if and only.
Yes. That's if and only if. So these are the bad primes. So what I did then is the following. So as I said, this matrix is huge, because the Bott-Samuelson module itself is huge. I mean, you see the rank in every step gets multiplied by 2. So this has already the rank as an S module 2 to the n. So this matrix will already have size 2 to the n. And but each entry is actually a product of roots, probably of n roots. I'm not. No, it depends on which entry you're looking at. It's a little bit more complicated. And then you have to reduce it to a one-dimensional situation. This gives you an integral matrix, but you can give an upper bound on each entry. And then you can give a stupid upper bound on each possible determinant, right? You just take the numbers, you form products and sums, and you forgot about minus signs and everything. And it's like, well, this gives an upper bound on each possible submatrix. This is the upper bound I calculated. The funny thing is that this matrix is invertible up to characteristic 2. You can show that as well. That means its determinant is a power of 2. But still, I mean, so you know that there's a lot of canceling going on when you calculate the determinant. Even though the numbers are very huge in this matrix, if you calculate the whole determinant, you have a multiple of, a power of 2. Which might also be huge, but still, it's a very, very strong property of the determinant. So this gives the upper bound. And Jordi found a specific 1-by-1 submatrix, which really is... So not all submatrices here play a role. But he found a 1-by-1 submatrix that's really describing a Lefschetz pattern that has C as its entry. So he calculated this number C, and he proved that it occurs as a relevant submatrix here. Rings of certain submatrices, I should say. And he showed that this submatrix is relevant. And then you calculated this number C, and it grows exponentially with the rank.
So the matrix being relevant, is it the same thing as saying it corresponds to a picture like that? Dots on the same line?
Yeah. So the relevant submatrices would be the following. So if you want to show this genericity property, recall that we have these generators here, and the only thing that you have to know is that, so this generator is up to a constant in the field well defined. So this might be one of our basis elements. And you take this, so this is one of the basis elements, and you project it. So what you want to show is that it's not contained in a submodule generated by these 3 generators. So you look at the submatrix, in this row, and with these 3 lines, and then you want to show it's 0. No, sorry, sorry. No, I mean you show that the component here is non-zero. So here you have a 1-by-1 submatrix that you want to show it's non-zero. Its rank is 1. So that would be one of the submatrices that play a role. And once you have that, you can delete this. You can ignore this basis and this basis, and then you show that this element is not contained in this line. That means the components in these 2 rows, whatever, are non-zero. You see, in that way, you construct the submatrices.
I understand. Because there are 2 lines in the same extremes, does it mean you get a 2-by-2 matrix, or is it larger?
Say it again.
Because in this particular picture,
Yes.
that type has multiplicity 2.
Right, right.
So does that mean that you're looking at a 2 by 2 matrix? Or you're looking at a bigger matrix?
So in this situation, you're looking at a 4 by 4 matrix. So you have a basis element. So you choose a basis in here and in here. So BS lower bracket X would have this 4 basis elements here, and BS upper X would have these 4 basis elements here. And then you look at the corresponding matrix. It's just each entry is a power of t.
Right, but you said that for peeling off, if something is, I mean, I'm just vaguely following, but you're going to start off with the top one, right?
Right.
So if the top
Right.
one splits off,
Right.
that part is taken care of, right?
Right.
And if that is the case, then what is the next one here?
Right. So so this is a 4 by 4 matrix. So let's call this 1, 2, 3, 4. So okay. Let me be a little bit more precise. So you have these 4 basis elements: 1, 2, 3, 4, and A, B, C, D. So what would be the right property of this matrix? So here we have a 4 by 4 matrix. I mean, it's a simple situation. These grow much bigger. So 1, 2, 3, 4, A, B, C, D. So we have this 4 by 4 matrix. So what do we want? This generator 1 is uniquely determined by degree reasons. It's the only that's sitting, so here, in lowest degree. And it should not be contained in the submodule, which is generated in degree -6 and -4. That means this entry, A1, should be non-zero. So the property here should be, this should be non-zero. And so next, we are looking only at the, so we divide out, we're working over a field. Then you can actually choose A in such a way that 1 is t to the LA, right? You can divide this by t to the 4 here and choose this as the basis element A.
Basically, somehow
So
you can start diagonalizing that matrix in a fashion.
yeah, exactly. It's kind of elementary divisors. You diagonalize this, and then you look at the elementary divisors.
Okay.
Right. So here, what I claim is important is then this submatrix, and then finally, I mean, this should be, yeah. So we're looking at elementary divisors. I could have said it before. A picture than this, but he found a 1 by 1 matrix, and he explicitly calculated this number. And I can, here he calculated. He told me he calculated these numbers in a cafe in Hong Kong. He had his computer, and he couldn't calculate it by hand. But he's also very smart in programming, and so he had his computer, and he let his computer calculate. And the first counterexample, just let me check the. So the first count. So the numbers he got. So that is in the case of SLN. So in the prime numbers, the prime numbers that the prime factor. So the biggest prime number dividing this one is the following. So he started with n equals 10. I mean, so far no one could calculate in SL10. I mean, this is so much easier than looking at representations of SL10 or moment graph sheaves also directly. This is very specific. 10, he got the number 3. He was disappointed. It's not a counterexample. In 14, he got 7. Still not. In 16, he got 13. Still not a counterexample. The Coxeter number is 16 in this case. But he got more excited, he told me. And then he got to 18 and he got 23. And he was overexcited. That was the first. Yes, that's the first time. And he said he was dancing in a cafe. That's what he said. And then it goes, I mean, now he actually constructed a machinery to produce counterexamples. It's an algorithm. You can go on and find as many counterexamples as you want, and you can also plug in, it's an algorithm, and you can change this algorithm a little and get completely different numbers. So that's really a world of counterexamples. And the biggest that he found so far is then n is 200. So for SL200, he found 1, 2, 2, 5, 8, 3, 7, 3, 6, 7. It's much bigger than 200, and it seems that these numbers grow exponentially. And he also, once he had these numbers, he looked at this algorithm more carefully, and he could also prove the following, namely the prime. The nth Fibonacci number so their prime, its prime divisors occur as torsion in SL 4n plus 7. So that holds for all n. That holds for all n.
Any n.
For any n, right. And there is, so the Fibonacci numbers grow exponentially. And there's a conjecture, an open conjecture in number theory, that infinitely many Fibonacci numbers are prime numbers. If this conjecture, so this is kind of expected. If this conjecture is true, we know that there's no polynomial bound for Lustig's conjecture. Okay, I think there's certainly much more to say, but thank you very much for your attendance. And I have to say, it was a pleasure for me to give these talks. And thank you very much again for the invitation.
Let's finish it off.
Yes. So it's been
It is wonderful.
it's
Thank
our
you.
pleasure. Hope you'll come back again for another.
Yeah,
meeting, maybe.
yes.
So thank you.